Hi everyone, my name is Kuvina and welcome to Relativity Part 5. The ladder paradox is the second most famous paradox in all of relativity, but in order to understand it, you need to know length contraction, and to resolve it, you need relativity of simultaneity. So make sure to watch the previous videos in the series. With that out of the way, let's get into it. So in the last episode, we derived an equation for length contraction, which states that as an object moves faster, its length is contracted along the direction of motion, and in the object's reference frame, everything else is contracted, including the space between objects. When we applied it to an example, though, it led to an apparent contradiction. Here's the situation. Imagine an 11-foot ladder passing through a 10-foot long shed. If the ladder moves at 0.6 c, its length will be contracted to only 8.8, which is less than the shed, meaning it will fit completely within the shed at some point. But in the ladder's reference frame, its length is still 11, and the shed is the one moving at 0.6 c, so its length will become 8. So this time, the ladder is longer, and it will never fit completely within the shed. So in the shed's reference frame it fits, but in the ladder's reference frame it doesn't. This is a contradiction, right? Well, it definitely goes against intuition, but in order to prove something is a contradiction, we have to take a step back and ask why. Why is this a problem, and what issues does it cause? To apply this to the ladder paradox, we need to properly define what it means for the ladder to fit. We'll say the ladder fits if and only if there's some time after it enters but before it leaves, during which you can close both doors of the shed. Now, why is this an issue? Well, what if we were to trap the ladder inside while it's moving? We know it fits in the shed's reference frame, which means we can close both doors. The ladder will inevitably crash through door 2 on its way out, but the important thing is that we were able to close both doors in the first place. The event of the doors closing still has to happen in all reference frames, including the ladder's, in which case it seems like they would have to phase through solid matter. But here's the thing, the event of the doors closing is not a single event, it's two events separated by a distance. This makes them technically different places. Now, relativity of simultaneity tells us that the only way to guarantee two events are simultaneous in all reference frames is if they also happen in the same place. The doors are in different places, so it's completely possible for them closing to be simultaneous in one reference frame, but not another. This is exactly what happens in the scenario. In the shed's perspective, the doors close at the same time, after which the ladder crashes through door 2. In the ladder's perspective, though, door 2 closes first, then the ladder crashes through it, and only after that does door 1 eventually close. This way, there's no phasing through solid matter, and every event still occurs across all reference frames, just in a different order. As a general rule of thumb, if two events are simultaneous in one reference frame, then to an observer moving past, the event further ahead will happen first. This is easy to remember if you associate the words early and ahead. We can figure out this rule with a simple scenario, which you might hear rephrased as the lightning strikes on a train thought experiment. 3 points in space, A, B, and C, are evenly spaced and stationary relative to each other. B sends signals to both A and C. These travel at the speed of light and arrive at the same time. But for an observer moving past, invariance of C kicks in. They'll see A, B, and C all moving to the left, but this won't affect the speed of the signals. So now, the signal sent to A has to cover more distance to catch up to A, while the signal sent to C has less distance to cover because C is also moving towards it. So in this reference frame, C receives the signal before A, corresponding with events further ahead happening earlier. So with this knowledge in place, we know that even though the doors are simultaneous in the shed's reference frame, door 2 actually closes first in the ladder's reference frame, which is why we don't get a contradiction. This explanation might be enough for you, but if you're anything like me, you'll find it less compelling to explain away apparent contradictions with relativity of simultaneity, and instead more compelling to construct your scenarios in a way where relativity of simultaneity doesn't apply. So that's exactly what I did. This time, for the sake of convenience, we'll say that the shed is 10 light seconds across, and the ladder is 11 light seconds. Instead of closing two doors, we'll replace door 2 with a solid wall, and door 1 will close as soon as the back of the ladder passes it. So now, our events in question are the door closing and the wall breaking. If the door closes first, it means the ladder fits, but if the wall breaks first, it doesn't fit. These events are still in different places though, which means their order can change depending on the reference frame. So if we want to find a contradiction, we need some way of converting the order into a single event. This is accomplished with detectors on both ends of the shed that detect our events in question. They're connected to a finite state machine, or FSM, in the middle. When the wall breaks, it sends a self-destruct input, but when the door closes, it sends a relax input, which puts the FSM into the relaxed state, and if it gets a self-destruct input while in the relaxed state, it does nothing. In the shed's perspective, the ignore input happens first, but in the ladder's perspective, the self-destruct input happens first. So surely this means the FSM self-destructs in the ladder's reference frame, but not in the shed's. If so, that would be a contradiction, because you can't have an event happen in some reference frames, but not in others. But it's at this point that we have to remember, instant communication is impossible. The fastest communication method is only light speed, so that must be accounted for in the scenario. Therefore, we'll say that both inputs come in the form of photon signals sent to the finite state machine. Now that we've incorporated the finite speed of light, let's run the numbers and see what happens. To visualize this, we'll use a line with squares representing points of interest. L1 and L2 are the endpoints of the ladder. D is the door, W is the wall, and F is the finite state machine. S1 and S2 are the relax and destruct signals respectively. This table will keep track of their positions and velocities. Starting in the shed's reference frame, we'll say that time 0 is when the door closes and sends out the relax signal. At this point, the ladder is only 1.2 light seconds away from the wall, and it's going at 0.6 C. This means that after 2 seconds, it will crash through the wall, causing the self-destruct signal to be sent out, by which time the relax signal has traveled 2 light seconds. After another 3 seconds, the relax signal is received, and the FSM goes into the relaxed state. Then after another 2 seconds, the self-destruct signal is received, but doesn't do anything, and the FSM doesn't self-destruct. Now let's switch over to the ladder's perspective. In this reference frame, the ladder is 11 light seconds, and the shed is moving to the left at 0.6 C, so its length is contracted to 8 light seconds. This time around, the wall breaks first, so time 0 will be when the wall breaks and sends the self-destruct signal. The door is 3 light seconds away from the left end of the ladder, which means after 5 seconds, the door will close and send out the relax signal. Remember, even in this reference frame, the signals still travel at C, so the self-destruct signal will have gone 5 light seconds to the left in this time. The gap from the wall to the FSM is only 4 light seconds, but since they're also moving, the signal is only halfway, and it will take another 5 seconds to catch up. But before that, it's only 2.5 more seconds until the relax signal reaches the FSM, because they're both moving towards each other. This puts it in the relaxed state, which saves it from destruction 2.5 more seconds later. So even though the FSM is halfway between the door and the wall, and even though the self-destruct signal is sent out first, the ignore signal is still received first, saving the FSM from destruction in this reference frame as well, so there's no contradiction. In fact, if you look at the delay between receiving the relax and self-destruct signals, you can conclude that the FSM ages at 0.8 times the rate in the ladder's reference frame, which is exactly what's predicted by time dilation. I think this example really shows the beauty of special relativity. Length contraction seems like it would cause problems, but when you remember relativity of simultaneity and do some calculations on an example, it all works out. There's still one thing we haven't tried though. In both this example and the one from episode 3, we used photons to transport signals. Since they travel at the speed of light, we ran into invariance of C, which is key to why these work. But what if we were to send slower signals, for example 0.2 C? In the shed's reference frame, the signals take longer to arrive, but the relaxed signal still gets there first. In the ladder's reference frame though, if velocities add, that would put both signals moving to the left, with self-destruct being 0.8 C and relax being 0.4 C. In that case, we would now calculate that the self-destruct signal arrives first and doesn't get ignored. This would be a true contradiction, so how can we possibly resolve this? Well, the thing is, in relativity, velocities don't add. Instead, they combine according to this formula. Applying it to the 0.2 C example, we can see that the speeds of the signals would actually become 5/7 of C and 5/11 of C, and with these numbers, the relaxed signal will again arrive first. With low velocities, this term on the bottom is so small that it's not meaningfully different than if they did add. But this formula does technically hold for low velocities. I don't know where I heard this example or why it's always stuck with me, but if a sheep runs at 2 meters per second on a platform that moves at 2 meters per second, then from the reference frame of the ground, the sheep's velocity is not exactly 4 meters per second. It's actually 3.9999999 9 more 9s 82. In the next episode, we'll take a look at how to derive this formula as well as some more of its implications. For now though, make sure to like and subscribe so that you'll see it when it comes out. Thank you for watching, and I hope to see you again soon. Bye!